last time we started to talk about logarithmic differentiation. So this time I would like to complete that discussion of logarithmic differentiation and move on to talk about the exponential function. So logarithmic differentiation, first and foremost, is a differentiation technique for functions of the form f of x raised to g of x. Mainly if there's a variable in the exponent position, then we want to use logarithmic differentiation. And so, at this point of calculus, I always ask the students to really think about what they're looking at and to be able to differentiate here. Here, I don't mean take a derivative. To be able to tell the difference here between here I have, a variable raised to a number versus here, you see, this is drastically different, but this is a variable raised to a variable. And the minute you see a variable upstairs here in the exponent position, we have to do the logarithmic differentiation. So that's the main thing, is to first understand when do we need to use logarithmic differentiation. So variable raised to a number, we use power rule. Number raised to a variable or variable raised to a power. So if I had 2 raised to the x, x raised to the x, cosine of x raised to the x squared, cosine of x raised to the sine of x, anything like that where you've got variables in the exponent position, we have to do logarithmic differentiation. So what is logarithmic differentiation? It's very straightforward, and I'll show you the example here. It's much simpler than the explanation. Starting with y equal to f of x, the first thing we do is take the natural log of both sides. Once we do that, then we want to simplify the right-hand side of the equation. The whole reason we took the natural log was so we can use properties of the log, like bringing down exponents. And then finally, once we've taken the log of both sides, simplified the right-hand side, then we can find the derivative using implicit differentiation. So let me show you, it's not a difficult procedure, it's just that when it's described verbally, it seems a little confusing. So let me just show you an example and you'll see it's not so bad. So let's find the derivative of x raised to the x. So I mentioned it last time, the number one thing I do not want to see students do is to say the derivative of x raised to the x, and then just to pretend like this is a variable raised to a number and use the power rule. So then they'd say, oh, bring down the x times x raised to the x minus 1. So this is, incorrect. This is something we should never do. Here I should realize, oh, I've got a variable raised to a variable. So let me use logarithmic differentiation. Starting from y equal to x, take the log of both sides. Now, the whole reason we took the natural log was now to simplify this expression. You see this x that's in the exponent, we can now bring it down in front. And x times ln of x, that looks like a function we're used to differentiating. X times ln of x, oh, that's a product. I can find the derivative with a product rule. So starting the equation, take the natural log of both sides, simplify the right-hand side, and now the next step is to differentiate. So what I'm going to do is take the derivative with respect to x on both sides of this equation. So for ln of y, be very careful here. So this is a place where it can be a little confusing. Remember that the function y is a function of x. Y depends on x, so this expression ln of y is actually a composition of functions. And so now when I do the derivative ln of y, I need to do the derivative of the outside. So you remember for ln of x, the derivative of ln of x is 1 over x. So here, if I'm trying to do ln of y as a chain rule, we do the derivative of the outside, so the derivative of the ln part, the derivative of ln of blah is 1 over blah, times the derivative of the inside would be y prime. So we'd end up with y prime over y. So here, the y prime is the derivative of the inside, and the 1 over y, that's the derivative of the ln part. We put that together, you get y prime over y. As I mentioned, for x times ln of x, we need a product rule. So I need derivative of the first times the second plus, now here I copy down the first function and times the derivative of ln of x. And here, as we know, as I mentioned here, derivative of ln of x is 1 over x. And now we put it together here. 1 times ln of x is just ln of x. X times 1 over x is 1. So I get y prime over y equals ln of x plus 1. Now be careful, we're not done yet. I'm looking for y prime. So I still need to take this y and move it to the other side and isolate the y prime. And here, don't forget on the right-hand side to put parentheses around the ln of x plus y, and we're going to multiply by that y. So that's why I do the next step. I move the y over times quantity ln of x plus 1. And the very, very last step is to replace the y with its definition in terms of x. We know y equals x raised to the x. And what we would really like is on the right-hand side to be completely just in the variable x. And so when we replace y, we get our derivative here. So the derivative of x to the x is x to the x times ln of x plus 1. And certainly, it's not obvious. It's not obvious to me when I look at it. And remember, this is all a result of the logarithmic differentiation. So let's do another problem. First, when you read this question, find dy dx if y equals cosine of x to the x squared. The first thing I want you to say is, aha, this is a derivative problem. Now let me take a look at what we're trying to differentiate. So now when I look at the function, I should say, oh, look, there's a variable in the exponent position. That means I need to use logarithmic differentiation. Here, this is clearly a case of a function that's in the form f of x raised to the g of x. Right? F of x is cosine of x. The exponent g of x is x squared. Here we must use logarithmic differentiation. There's no other option. I cannot use the power rule. Remember, I cannot use the power rule. So starting with y equal to cosine of x raised to x squared, take the natural log of both sides. Now it's really important that we understand the whole reason we took the natural log was so that we can use the properties and simplify this natural log of cosine of x raised to the x squared. We can bring the x squared down in front. That's a property of the log, allows us to bring the exponent down in front. And that's the whole reason we took the log. We have this problem when we have a variable up in the exponent, but the log allows us to bring that down. And now I no longer have a variable up in the exponent. So we're ready to differentiate now. We've completely simplified this, log expression. So as before, remember, ln of y is a composition. Y itself is a function of x. So this is like ln of f of x, and I need a chain rule. Derivative of ln of blah is 1 over blah. So here, derivative of the outside would be 1 over y times the derivative of the inside is y prime. Put those together, you get y prime over y. On the other side, I'm doing a product rule. So what you should see is x squared being multiplied by the natural log of cosine x. And so product rule, I do derivative of the first times the second. So here's the derivative of the first, which is 2x, times ln of cosine x, plus I'm going to copy down the x squared. And then for the derivative of the natural log of cosine of x, so for the derivative of this expression, natural log of cosine of x, what you should see is a composition of functions. The cosine of x function has been put inside of the natural log function. So here I need a chain rule. Derivative of the outside will be derivative of ln of cosine. Ln of blah, derivative of the outside will be 1 over cosine of x. that would be the derivative of the outside, times the derivative of the inside. The inside function is cosine, and the derivative of cosine is minus sine. So here, the derivative of ln of cosine of x here is minus sine over cosine. And so that's where this expression is coming from. Minus sine over cosine, it's the derivative of the term directly above it. So yeah, now we just kind of put it all together, you know, so sine over cosine is tangent, the minus, I move here in between the two terms, so I'm able to simplify this as y prime over y equals 2x times the natural log of cosine of x minus x squared times the tangent of x. Remember, I'm trying to solve for y prime. So my last step here is I'm going to take the y that's in the denominator on the left-hand side and move it to the other side. Of course, I remind you to put parentheses around everything that's on the other hand side because the y is multiplying that entire expression. So when I move the y, I get y prime equals y times 2x natural log of cosine x minus x squared times the tangent of x. Very last step, replace the y with its definition as a function of x. So I replace y with cosine of x raised to the x squared. And that's my final answer. So that this huge mess here is now the derivative that we're looking for. So the derivative of cosine raised to x squared is x cosine raised to the x squared. So here, be careful, I factored out a common term. There's an x that's a common term, and I factored that out also. That's where this x is coming from. And you'll notice there's no x here, and this dropped 1 degree because I factored out the common term. Yeah, so the derivative of cosine raised to the x squared is x cosine of x raised to the x squared times 2 times the natural log of cosine minus x times the tangent of x, right? It's the answer we all thought. That's what we would have guessed if we had to, right? So, you know, to me, one of the most important parts is to realize that for this type of function, we must use logarithmic differentiation. That's really, if we don't get that first step, then, you know, everything else we write down is going to be incorrect. The actual logarithmic differentiation is not that difficult. So here, let's do another example. So this example is slightly different because we're asked to find the derivative of y equal to the positive square root of x over x squared plus 1. But note that we can actually find the derivative of this function. So if I write the function in this way, x, quantity x divided by x squared plus 1, the whole thing raised to 1/2. If I write it this way, we can absolutely take the derivative of this right now without any additional techniques. I would do a chain rule. So this is a composition. The inside function is x over x squared plus 1. The outside function is, you know, the square root being raised to the 1/2. So I'd do a chain rule. The derivative of the outside, you'd bring the 1/2 down times x over x squared plus 1 raised to the 1/2 minus 1 times for the derivative of the inside, then we'd have to do a quotient rule. So it's doable, but it's kind of a mess. You got to do this, you know, the chain rule with the derivative of a root function, and then for the derivative of the inside, you're doing a quotient rule. So here, we're specifically asked to do this using logarithmic differentiation. In fact, you can do any differentiation problem with logarithmic differentiation. It's just that for something that's very easy, like y equal to x or y equal to x squared, we wouldn't want to use logarithmic differentiation. Here, let's see what happens when we do logarithmic differentiation. I claim this to make the problem a lot easier and that we won't have to worry about the quotient rule. So starting with the original function, I take the natural log of both sides. I write the square root of x over x squared plus 1 as x over x squared plus 1 quantity to the 1/2. And here's my natural log. Now, the whole point of taking a natural log is to use the properties. So I'm going to bring the 1/2 down. And we have another property that says ln of a over b equals ln of a minus ln of b. And so here, ln of x divided by natural log of x, natural log of x divided by x squared plus 1 I can write as a difference. I can write it as ln of the numerator minus ln of the denominator. That's a property of the natural log. Now that we've completely simplified the right-hand side, be very careful. Natural log of x squared plus 1 does not simplify to anything. So one big mistake I'll see is a student might write natural log of x squared plus 1 equals natural log of x squared plus natural log of 1. That's false. There's no identity for the natural log of a plus b or a minus b. There's only an identity for the natural log of a times b, natural log of a divided by b, natural log of, x raised to the r, but not natural log of a plus b or natural log of a minus b. So that's something that's really important, that you don't try and, falsely simplify a natural log of x squared plus 1. There's nothing to be done there. Now that it's completely simplified, we can differentiate. So here's the original equation where I've taken the natural log and simplified. I'm going to take the derivative of both sides. As you know, the derivative of natural log of y is y prime over y. And on the other side, I'm just taking the derivative of each of these terms individually. The derivative ln of x is 1 over x. The derivative ln of x squared plus 1, I'm doing a chain rule. The derivative of the outside is 1 over x squared plus 1 times the derivative of the inside, or 2x. The derivative of x squared plus 1 is 2x. So you should see the derivative of x squared plus 1 divided by x squared plus 1. That's your chain rule. And finally, I'm going to move this y over because I'm not looking for y prime over y. I'm just looking for y prime. Last step here, I'm just going to replace this y with its definition as a function of x. So last step, I'm going to replace that y, and then, we're done. So I think I combined these two fractions, but you don't have to. And I don't even know why I did it. I guess I just felt like it. I just threw them together just because I felt like it, but you certainly don't have to. Once we replace the y here, we're done. That, once you replace y with this expression, the square root of x over x squared plus 1, we found the derivative. What you should notice here is we didn't have to do a quotient rule. I would rather do this than a quotient rule. Even when we do a quotient rule, we then have to simplify the quotient rule, which is also kind of a pain in the butt. So here, we didn't have to do quotient rule. We didn't really have to try and simplify the quotient rule. So there were some advantages to this, So yes, logarithmic differentiation will become, a fundamental technique that we'll use a lot. So we'll use it again here in this next section. So here I ended this set of lecture slides with I just wanted to put the graphs on there. So one graph is the definition and the other of natural log of x, and the other graph is the actual graph of the natural log of x. So these area values that are showing up here under the curve, they would appear on the y-axis. And so I'll let you compare the two graphs here and just think about one's the definition and one's the actual graph of the function. So that ends our discussion of 5.2. And so now we want to talk about the inverse of the natural log function, which is known as the exponential function. So as you remember, the exponential function was defined as this weird integral thing, the integral from 1 to x, 1 over t dt for x greater than 0. That's just the definition. And then using the natural log, we were able to define the number e, the Euler number. It's the number such that ln of e equals 1. Another way to say it is that the area under the curve 1 over x between 1 and e is exactly equal to 1. So now we can use the Euler number e to build an inverse. So let's define the natural exponent function now. Just like we had the natural log function, now is our natural exponential function, y equal to e to the x. Now you remember, a function is an input-output machine. So what I need to do now is to give you the recipe for this function. That is to say, for any input, I need to tell you how to find the output. So suppose b is our input. So for any real number b, for any input b, I want to define e to the b to equal the number a, where, so now here, how do we find a? Where ln of a equals b. So let's think about this very carefully. Remember, the natural log function is defined as integral 1 to x, 1 over t dt. We can find the natural log, we can evaluate the natural log function using limits of Riemann sums. So I can find ln of a. And also remember that the range of the natural log function is all reals. So what does that mean? That means for any real number b, I should be able to find a number a such that ln of a equals b. And there'll only be one number because it's 1 to 1. For every input, there's only one output. And here, the entire range is all the reals. So for any real number, I should be able to find an input a such that ln of a equals b. So now reverse that relationship, reverse the input-output relationship. So now for the input b, let e to the b be equal to the output a. If and only if ln of a outputs b. And so we've just reversed the relationship, just like we've reflected across the diagonal line, basically. So now I formally claim if our function is the natural log, then its inverse is e to the x. And note, for example, there's a definition of an inverse. We have to be able to show that f composed with f inverse gives you back the original input x. So let's check that here. Here, f of f inverse of x, and I'm doing the trickier direction. The other direction, f inverse of f, that's easier, okay? So here, f of f inverse of x is the natural log of e to the x. So now I want you to watch what happens here. We bring the x down. And now, the only way this will equal x is if ln of e equals 1. And by a stroke of luck, not really luck, ln of e does equal 1. And so I get back x. So, I believe this is exactly where the Euler number was discovered. I believe, mathematicians were trying to construct the inverse. And they said, okay, we've got ln of e to the x, or ln of some number to the x. Then they said, okay, it equals x times ln of that number. And then they realized, okay, the only way this is now going to work if this ln term happens to equal 1. And so we need to find a number such that the ln of that number equals 1. And oh, by the way, let's just call it something. Let's call it e in honor of Euler, the Swiss mathematician. So I think it's at this stage where they realized, oh, you know what? We really need a number so that the natural log of that number equals 1. And that's, this is why I think the Euler number was discovered or invented, or however you want to think about it, to make this composition work so that we can see that you get back the original variable. And this does turn out to be an inverse. You can also, as I said, the composition the other way is just by definition. You can try that one. So just a notational comment, some books will write exp of x instead of e raised to the x for the exponential function. So now we've got a new function. We're starting calc all over again, right? What's the domain? What's the range? What's the graph? What's the derivative? What's the antiderivative? How do we do limits? So now here I catalog all those facts for you. The graph of the function for e to the x and ln of x is incredibly useful for knowing all of these facts. Like all of these facts here that I've written in words, you can just see by looking at the graph. That the domain is minus infinity, range is 0 to infinity. Yes, I can see that just looking at the graph. Y equal e to the x is continuous. Certainly I can see that from the graph. And remember, we get the graph by reflecting the graph of the natural log function about the line y equal to, that's supposed to be diagonal, about the line y equal to x, right? We reflect that. So that's how we know what the graph even looks like. And remember, when we say a function is continuous, we're really telling you something about how you can evaluate limits with that function. So to say it's continuous is to say we can evaluate limits just by plugging in the number. It has the direct substitution property. As x goes to the right, e to the x blows up. You can see that from the graph. The limit of 1 over e to the x as x goes to infinity, the denominator will blow up, so the whole limit will be 0. Another way to think of it is we're looking at the graph e to the minus x, which is just the e to the x graph reflected about the y-axis. And so you could even think of this as a limit pertaining to the e to the minus. And you can see as x goes to infinity, e to the minus x will go to 0. And as x goes to negative infinity, e to the x will go to 0, and e to the minus x will go to infinity. I erased it right here. So e to the minus x. And so, you know, rather than learn these facts from me, I just make sure I know the graph. And then from looking at the graph, I can see all that information that's written right here. Similarly for the natural log function. So, okay, let me now write down some properties here. As you remember, one of the most important things about working with inverses is to be able to go back and forth. And so I want to show you that here when f of x is ln of x and the inverse is e to the x. So for example, the fact that they're inverses implies that e raised to the ln of x will give you back x, provided x is in the domain of the natural log function. So this is a very important property that, you know, we'll use a lot. Another important property is that the natural log of e to the x is equal to x. So here what we're seeing is that e and natural log are canceling each other out and just giving us back the original input variable. Here, if y equals e to the x, we are allowed to take the natural log of both sides, and what we end up with will still be equal. This is because the natural log is a one-to-one function. And what does that mean? For every input, there's only one output. So here, if these inputs are equal, and we plug them into the natural log, their outputs have to be equal. And this is a way of reversing the problem. So what you should see is, here, the unknown variable, let's say it's x, it's up in the exponent position, and now it's no longer up in the exponent position. And going the other way here, suppose I have ln of y equals x, we can exponentiate both sides to undo the natural log. Here, if I e both sides, I e the ln y, e the x, the e and the ln cancel and you get y back. So this would be if my unknown was inside the natural log. You know, suppose I had the equation ln of x equals y, then the way I would get the x out is to use the exponential function. And I'll do an example here in 1 second. In general, this is what we're saying. And this, what's in the box here is the same as what's in the box up there, that if, you know, if one of these is the function, then we can reverse the argument. To go from y equal e to the x to ln of y equal to x, just apply ln to both sides. Just like to get from this equation to this side, just apply f to both sides. To get from ln of y equal to x to y equal e to the x, exponentiate both sides. Raise both sides to the e power. Just like here, if I want to get from this side of the equation to the other, apply f inverse to both sides. It's the same idea, and you should practice going back and forth, you know, from one equation to the other. And we will do this a lot, not just with the exponential function. We will do this idea a lot, not just with the exponential function, but we will do it when we look at the inverse trig functions. You know, we will do it when we look at inverses in general. So let me do a limit problem. Calculus, we started with limits. So I know this is a limit problem. And I know the first thing to try is to plug it in. And we know as x goes to infinity, e to the x is going to blow up to infinity, right? Look at the graph. Let the graph help you figure out your limits. So here, when I actually apply the limit, the numerator blows up to infinity. The denominator is blowing up to infinity. I have an infinity over infinity type problem. And so here, infinity over infinity means we need to do something. So you can do dominance of powers. I'll show you that second. Here, let me show you. formally, mathematically, what we would do is factor out the term that's blowing up to infinity in the numerator and denominator. In this case, it's e to the x, which I factored out. Then we cancel. Then we apply the limit. When we send x to infinity, e to the x blows up. So 1 over e to the x goes to 0 because you get 1 over infinity. So here in the denominator, also 1 over e to the x goes to 0. And so we can calculate the limit is just 2. Or we could do this with dominance of powers. So here, basically, I only want to look at the quotient of the coefficients of the terms that are blowing up to infinity. The 1 and minus 1 here, I can ignore. So here, I made the 1 and minus 1 that were written here, completely ignore. And so now I'm just looking at the quotient of the terms that are blowing up to infinity in the numerator and denominator. I do algebraic simplification, cancel the e to the x, apply the limit, we get the same answer, of course, which is 2. And note that just to tie it all up, with the stuff we studied in chapter 1, we can conclude y equal to 2 is a horizontal asymptote of this graph. Now be careful. To find horizontal asymptotes, we need to also look at the limit as x goes to negative infinity. So let's do that. This limit is very easy. So this is one of these things about the exponential function. We should not be tricked. Remember, the graph of the exponential function looks like this. So if we send x to negative infinity, this end goes to 0. E to the x goes to 0 as x goes to negative infinity, so that when you apply the limit, these terms just disappear. The 2e to the x and e to the x, they just go away. They're just multiplied by 0. I'm just left with minus 1 over 1 or just negative 1. And so we have another horizontal asymptote. The big mistake I can imagine is for this limit x going to negative infinity, I can see a student just doing dominance of powers because they think e to the x is dominating. In fact, it's not. It's the opposite in this case, right? Both the exponential terms are being dominated by the constants, minus 1 and plus, because they're disappearing to 0, the exponential terms. So if you use dominance of powers here, it will result in the wrong answer. So be careful. And, it's just about knowing how e to the x behaves. If the x gets very large, e to the x gets very large. If x goes to negative infinity, e to the x goes to 0. It's just knowing that behavior of the exponential function. These next two examples are just pre-calculus examples. So I think it's important just to remind you of this. So I want to solve for x, and I have this equation that involves all of these logarithmic terms, okay? So for me, the first step for me is to isolate the term that contains the variable I'm looking for. So here I'm going to isolate the natural log of x minus 1 by moving the negative minus ln of 2 to the other side. And it becomes plus when I move it over. Now that I've got the ln of x minus 1, I've got the term containing the variable that I'm looking for. The way I think about it is the x minus 1 is trapped inside the natural log. And now the only way to free it is to exponentiate both sides. So I'm going to raise both sides to the e. I'm going to e both sides. So on the left-hand side, I have e raised to the ln of x over 1. And on the right-hand side, I have e raised to the t plus ln of t plus ln of 2. So on the right-hand side, the whole point was to use the fact that they're inverses. So here, I now just have x minus 1. The inverses, the e and the ln cancel each other. On the other side, just to remind you, e raised to the x plus y equals e to the x times e to the y. So here, I'm able to write e raised to the t plus ln of 2 as e to the t times e to the ln t times e to the ln 2. E to the ln of t we can simplify as t. E to the ln of 2 we can simplify as 2. E to the t, we cannot simplify that. That just stays as e to the t. My last step here is I'm going to move this -1 over to the other side. When I move it, I get a +1. And so my final answer is 2 times t times e to the t plus 1. So as I said, there was no calculus there really. I mean, I guess so in the fact that we need calculus to define the natural log. But this is the type of problems we've done in pre-calculus. Similar thing, except my unknown is trapped in the exponential position instead of inside of a natural log. So here we have the equation 100 times e raised to the 10x equals 200. And we want to solve for x. And you can see here, the way I like to think about it is that 10x, it's trapped up in the exponent position. So first, as I said, I personally like to isolate the term that has the variable I'm looking for. So the e to the 10x contains the x. So I isolate the e to the 10x by dividing both sides by 100. Now I'm going to free the 10x that's stuck in that exponential position by taking the natural log of both sides. This is what's really nice about the natural log, is now I can take this 10x and bring it down in front. And it's no longer in the exponential position. That was the issue. I don't know how to deal with variables in the exponential position. With the natural log, we don't have to. So I bring the 10 down. And of course the ln and the e cancel, ln of e is 1. So then you have 10x is equal to ln of 2 and then solve for x. So this is pre-calculus, but sometimes it's confusing. Wait, how do I do the algebra? How do I solve for the unknown? So this is just meant to remind you how that works. So since this is a calculus class, let's talk about the derivative. So for y equal to e to the x, we'll use logarithmic differentiation to find the derivative. So starting with y equal to e to the x, take the natural log of both sides, and then simplify the right-hand side. Here, natural log of e to the x, we know we can bring the x down, this x times ln of e are just x. So we're able to simplify the function. So look, I've converted the problem. I converted y equal to e to the x. I've converted it. It's the same problem, but I've rewritten it now as ln of y equal to x. So this is typical of how we work with inverses. I took y equal to e to the x and inverted the equation, applied natural log to both sides. Now differentiate. I want the derivative of the left-hand side is equal to derivative of the right. Derivative ln of y, remember y is a function of x, so I need a chain rule. So I have derivative of the outside, which is 1 over blah, derivative ln of y, times the derivative of the inside. The inside was y, so the derivative is y prime. Obviously, the derivative of x with respect to x is just 1. Remember, I'm looking for y prime, so let me move the y to the other side, and we get y prime equals y. And last step is to remember that, y actually equals e to the x. So here we have y prime equals e to the x. That is to say, we can conclude that the derivative of e to the x is itself, the derivative of e to the x is e to the x, which is kind of strange, but, interesting. And here, so we've got a new derivative formula. And so what I like to do is also write down the chain rule version of the new formula. So here, this would be if we had e raised to some function of x, not necessarily e to the x, but maybe e raised to cosine of x. So in this case, we do derivative of the outside. The outside function is e raised to something. And the derivative of e raised to something is just the same. Just copy it down, e raised to the something. So derivative of the outside is just the same, e to the u of x, times the derivative of the inside, which is u prime. So that's how we get that chain rule version of the derivative. So I do want to mention, another important thing that's happened is that this equation is an example of our first bona fide differential equation. It's an equation that only involves the unknown variable or derivatives of the unknown. Here, the unknown is y. And the equation only involves y or y prime. And here we're able to solve it. We know y equals e to the x. So This is our first differential equation that we're able to solve. And this is the first example of an equation that feeds information back into itself. So this part is really important. I want you to look and interpret this as a feedback loop. Okay, so suppose starting with y, suppose, for example, y is a positive number. If y is a positive number, then y prime is the positive number. If y prime is a positive number, that means y is increasing, so this y gets bigger. But if this y gets bigger, then y prime becomes a larger number. If y prime is larger, that means the function increases even faster, and so y becomes even larger. And you see, these two things are just feeding back and forth into each other. And that completely explains the graph. In the graph, what you see is the slope is proportional to the height. That is to say, the slope of the function gets steeper as the altitude of the function gets higher. This is exactly a scenario where we're in a plane and the altitude is going up, and we're constantly pulling the nose of the plane up. We're making it pitch up as it's increasing altitude continuously forever. You know, so that explains the graph of e to the x as a feedback loop. And we'll talk about the feedback loop idea more when we talk about differential equations. So let's practice our derivatives. So here, e to the x squared plus 1, you must see a composition. The outside function is e, the inside function is x squared plus 1. Here, this is e of x composed with x squared plus 1. So I'm going to do the derivative of the outside. The derivative of e to the blah is just e to the blah. So I copy down e to the x squared plus 1 times the derivative of the inside, so times the derivative of x squared plus 1, which is 2x plus 0. And now I just do the math and put it all together. And so there's my derivative using a chain rule here of e to the x squared plus 1. So it's really important that we not use a power rule. It's very common. I've seen this, you know, that people will bring the x squared plus 1 down and then say this is e to the x squared plus 1 minus 1. I get why they're doing that, but it's still wrong. Do not use a power rule here. This is its own thing. We have to use, you know, you could use logarithmic differentiation if you wanted. That would work here, no problem. I mean, that's how we found the derivative of e to the x in the first place. But do not use the power rule. So let's do another derivative here. I just wanted to remind you of the old quotient rule. It's been a while, you know, quotient rule, our good friend. So here we have y equals e to the 2x over x, find the derivative. So as I said, we first recognize we're trying to find the derivative of a quotient of functions. So I need a quotient rule. And of course, I have to have my quotient rule memorized. So I square the denominator first. Then I need the derivative of the numerator. This is a composition. This is e to the x composed with 2x, okay? The inside function is 2x, the outside function is e. So the derivative of the outside, the derivative, the e to the 2x part is just e to the 2x, times the derivative of the inside, which is 2x. The derivative of 2x is right here, which is 2. Then I multiply by the denominator. Then I have a minus sign. And now I want the derivative of the denominator. Derivative of x is just 1 times the numerator, which is e to the 2x. So that's my full quotient rule. Only thing left to do now, I can see, is just to factor out the common term, which is e to the 2x. I factor out a common term. There's our derivative. So nothing has changed, except now we have a new differentiation rule for e to the something, right? E to the u of x, derivative of e to the u of x is e to the u of x times u prime of x. And that's something now we need to slowly start to memorize. Here's a nice derivative problem because this really uses a lot of previous material and new material. Even though we see an integral here, we know this is actually a derivative problem. And we're not going to integrate this and then differentiate it. You know, that doesn't make sense. Here we can use the fundamental theorem of calculus. This is one of those weird integral defined functions. Remember, x here is the only input variable. T is the variable of integration. You can replace it with any letter other than x. It doesn't matter. So fundamental theorem of calculus says the derivative and the integral are going to cancel each other out. I can take this ln of x and plug it in for the t. Here, because the upper bound is not just an x, I need to use the chain rule version of fundamental theorem. So I'm going to do the derivative of the outside. So the integrals cancel. I replace the t with ln of x times the derivative of the inside, where the inside function is ln of x. So the derivative of ln of x is just 1 over x. So there's the derivative of the inside. And so, you know, I just clean this up a little bit. The e to the ln of x, I simplify that, write that as sine of x, and then divided by x. And so here we see the derivative is sine of x over x. Something to keep in mind is sine of x is not an algebraic function. It does not have an antiderivative. So doing something like this would be really the only way to come up with an antiderivative. It's the same issue with 1 over x. We had to invent natural log of x, you know, in the same way. So here I put this problem on here just to mess with you in terms of the notation. I really wanted to mess with your eyeballs. I really want you to train your eyeballs. Think about what you're looking at. This first expression, that's x raised to the e. That's like x raised to the 2.7. That's a variable raised to a number. I would use a power rule to integrate that. This second expression, this is e, a number, raised to pi x. You know, I have an x up in the exponent position. I'm not going to use a power rule here for the derivative of e to the pi x. Okay? And of course, at the very outset, I have a product. So I'm first going to do a product rule. Here's the derivative of the first term using a power rule, because x to the e is the same as x to some number, x to 2.7, blah, blah, blah. It's x to a number. And there I use the power rule. And then, of course, I copy down the derivative of the first times the second plus, and so now I copy down the first function, right, plus the first function times the derivative of the second. So let's take a look at this. Here for e to the pi x, that's like e to the u of x. So the derivative would be e to the u of x, which is right here, e to the pi x, times u prime. Here u of x is pi x, and the derivative of pi x is just pi. So yeah, I just did this problem. It's not difficult, but the notation is weird looking. You know, for the x to the e, we are doing a power rule. For the e to the pi x, we are not doing a power rule. We're essentially doing the derivative that we got from using logarithmic differentiation. Now, just some algebra stuff. I noticed there's a common term. So I noticed that you have x raised to the e minus 1 and x raised to the e. So they're both base x. That's a common term. So I'm going to factor out the lowest power, the x to the e to the minus 1. And hold on here. Actually, let me combine some terms. I forgot. Here, I also noticed the e and e to the pi x, that can be combined. E is like e to the 1. And so when you have the same base, you can add the exponents. So e times e to the pi x is e to the pi x plus 1. Just now doing algebra. You know, there's no more calculus anymore. We took the derivative already. So now, as I said, I'm going to factor out the common term here. X, e to the minus 1 is a common term. Here's an x to the e. And the other common term that I want to factor out is e to the pi x. So here's another e to the pi x. And I'm factoring out the lowest powers of these common terms. So there's my x, e to the minus 1, e to the pi x. And then I did the algebra on the inside. I'll let you make sure that algebra looks good to you. But yeah, that's how that ends. You know, and I purposely like this problem because when folks see stuff like this, it messes with them. When people see x to the e minus 1, that seems to mess with their brain. X to the e, you know, x to the pi versus pi to the x. How would you differentiate both of these? You know, So that's why I wanted you to do this problem, just for you to get used to this weird kind of notation. Let me just make one final comment here and stop. Since the derivative of e to the x is e to the x, then the antiderivative of e to the x is also e to the x, right? We only write this statement if the derivative here of this right-hand side, e to the x plus c, if the derivative of that equals the integrand e to the x. And certainly that's true. And I went ahead and wrote the u substitution version. So after u substitution, if I have e to the u du, then I can replace that with e to the u plus c. And then typically last step is to replace the u here, with what we originally substituted it for. So with e to the 2x, if we let u equal 2x, the problem is I don't know how to integrate e to the 2x, but I do know how to integrate e to a single variable. So why don't we just make 2x equal to a single variable? That's eventually what happens here. So du is 2 dx. And so now I can convert the integral. I don't have a 2 dx, so I multiply by a 2 and I divide by 2. Or you can solve for dx. Dx would be du over 2, and that would give you the 1/2 in front. And so now I can convert this. So now I have 1/2. E to the 2x becomes e to the u. The 2 dx becomes du. I know the antiderivative of e to the u is e to the u plus c. And here the 1/2 technically distributes to the c, but 1/2 times a constant is just another constant. So here I just have 1/2 e to the u plus c. And finally, I replace the u with what we originally substituted for. Remember, the original problem is in terms of x, so I need the answer to be in terms of x. All right, so I'm going to stop right here. By the way, we can generalize this problem. In general, if I have antiderivative e to the nx, so now instead of 2x, I have nx, where n can be any number. E to the 3x, e to the 4x, e to the pi x. The answer is always going to be e to the nx over n plus c, okay, for any constant n. So I'm going to stop right here, and I'll pick it up right here on Monday, but please feel free to read ahead. So I'll stop right here.